We have 100 gigawatts of solar technologies on the grid today, 3 million systems, and we're working toward hundreds and hundreds of gigawatts of additional solar on the grid.
As we transition to systems that have greater fractions of generation provided by renewable power, we need ways to deal with that intermittency. We have a project focused on developing next generation power systems that are based on power electronics inverters. We want to model, analyze, design the future inverter-based grid based on renewables. The traditional inverters that are on the grid today are what are called grid following. Those are based on the assumption that you have this stable grid that is already provided to you. A grid forming inverter completely dispenses away with the notion that you need an energized, stable system that you're connecting to and following on.
We're developing technologies that can enable solar, wind, and battery storage to not only keep the grid as reliable as it is today, but to enhance the grid's ability to recover quickly in the event of a natural disaster.
A storm or a heat wave end up having similar outcomes. You'll get a fault on the system. So you can have parts of the grid that can become segmented. Generators can become overloaded. With grid forming technologies, you could have massively distributed generation and storage just littered across the entire grid, stabilizing the grid at all scales simultaneously.
Grid forming inverter technologies are really exciting in their opportunities to provide essential services and to bring power back as quickly as possible when the grid goes down.
We need to unify the operation of next generation power electronics inverters with traditional generators. If we bring these two generations of technology together, then we can ensure that our grid is stable not only today, but as it evolves.